So what is the transfer function of this system? And how does it compare with this transfer function of this system that does not have a delay? To know that, we will have to find the Laplace transform of a delayed signal. Let me draw here a signal and its delayed version. F of t is a signal. F of t minus theta is the same signal with a delay of theta. Let us suppose that the Laplace transform of f of t is uppercase F of s, as usual. What will be the Laplace transform of f of t minus theta? By definition, it will be the integral from 0 to infinity of the function of which I want to know the Laplace transform multiplied by the kernel, which is this, and we integrate in order to t. Notice that the delayed signal until time instant theta is equal to 0. As a consequence, I can put here a Heaviside function so that the integration, in fact, only begins at this time instant. Remember that a Heaviside function with argument t minus theta behaves like this. Our Heaviside function will begin to be equal to 1 here at theta. Until then, it is 0. And I can put this Heaviside function here because of this delay. Until theta, there is nothing there. Now, I will carry out a variable change. I am going to say that tau is equal to t minus theta, this thing here. Here I have t. T will be equal to theta plus tau. The differential of t will be the differential of tau. This is a constant, so it doesn't matter. When t is equal to 0, then tau will be equal to minus theta. When t is infinity, then tau will be infinity too. Thanks to this variable change, I can rewrite this integral. The integral from, now we're not integrating in t, we are integrating in tau, so we'll go from minus theta to infinity. Here we will have the Heaviside function of tau, f of tau, and an exponential of tau plus theta. The differential now is that in tau. We began our integral at minus theta, but we have here again a Heaviside function. Even though we are integrating from here on until infinity, because of this Heaviside function, which is only equal to 1 from 0 on, we do not have to integrate this little bit here from minus theta to 0. We can simply write the integral from 0 to infinity of f of tau. The Heaviside function is gone, now that it has served its purpose, multiplied by these two exponentials. This one has nothing to do with the integration variable. I will bring it out, and what will be left is by definition the Laplace transform of f. So, the Laplace transform of my delayed signal f is f of s multiplied by this, which is the Laplace transform of the delay. It is a complex exponential with the delay here. In any case, knowing this, I can now write the transfer function corresponding to this differential equation. Applying the Laplace transform and remembering that initial conditions are 0, I will have this exponential here, and thus the relation between output and input will be as follows. Notice that this transfer function is not the ratio of two polynomials in S. We have this term here, which is not polynomial. The Laplace transform of the delay has this effect in transfer functions in continuous time.